All right, everybody, welcome back to another episode of PH Drizzle. This is the show where I talk about whatever I'm thinking about these days, but sprinkle in stuff that I learned from my PhD program. I'm your host, Kirby White. I would be Dr. White by now if I didn't keep getting distracted by stuff like this video. So let's all have a little fun with it and jump right in. This particular video is inspired by just more articles that I've been seeing pop up on my social media feeds lately about vaccine ineffectiveness. Now that lots and lots of people around the world have been vaccinated, there's a lot of articles that are coming out showing how thousands of those people have still gotten COVID, been hospitalized, been ventilated, or even died from it. And so if we collect all of this information together, we can come to sort of this hypothesis that if thousands of vaccinated people are getting infected, being hospitalized, and dying of COVID, then the vaccines must be ineffective, possibly even dangerous. So what I want to do with this video is talk about how a scientist would approach a question like this, looking at the differences between a group of vaccinated people and a group of unvaccinated people. Unsurprisingly, the term for this kind of research is between group differences, or this is the type of effect that we're looking for. Just is there a difference between one group and another group of subjects, of units, sometimes they're called. And this could be anything, like if we take a group of adults and children, is there a difference in their height when standing? Or two species of apples, do they vary in their weight? Or if a group of people are wearing their seatbelt and a group of other people are not wearing a seatbelt, which is more likely to be safe in a car accident? And so let's think about this particular example a little bit more, because it's actually a really good analogy, I think, for vaccinations. So let's imagine that we do a study and we go to Harborview, a major hospital in the King County area, and we collect some data. We just watch the patients that come in for a few weeks. And eventually we have 200 car crash patients that have come in, and 180 of them were wearing their seatbelt and only 20 were not. Now, in this group of people, it's really easy to jump to the conclusion that, well, since 90% of the people that were hospitalized after a car crash were wearing their seatbelt, when only 10% weren't, well, then seatbelts must actually make car crashes worse. And if you're thinking, maybe I just need to never wear my seatbelt again, hang on. Don't fall into the base rate fallacy. So the base rate fallacy is what happens when we take a set of numbers and sort of ignore the context, ignore other factors that are relevant to interpreting that data, and we come to an incorrect conclusion based on that. And so what I want to do in this video is talk about how to be a little bit of a statistics superhero and avoid falling into the base rate fallacy by using the odds ratio. That's what we're going to talk about in this video. So a little bit of nerd stuff, some theory before we jump into actually the math of odds ratios, is a scientist first has to think about the natural phenomena that they are observing. In this example, it was car crashes, and decide what kind of data best represents that phenomena. And this is a theoretical a decision that needs to get made. And in 1946, maybe I should do another video on this. In 1946, Stanley Stevens, S.S. Stevens, proposed the Stevens typology of data to represent different natural phenomena. He was an experimental psychologist and really influential in developing research methods for psychology. And this is not the only framework, but it's probably the most common one that researchers use. And so Stevens said that those natural phenomena can best be put into these four categories: ratio, interval, ordinal, and nominal. And you could sort of crudely put them into these quantitative and qualitative buckets, but don't spend too much time thinking about that. But without going into what all of these different types of data are, I want to say that it's really important to know what data you're working with, because it affects the kind of statistics and the calculations that you do. So depending on the relationship between the type of predictor and the type of outcome you're looking at, you'll calculate a different effect size. And an effect size really just asks the question, what's the magnitude of difference between two data sets? And so we'll take that effect size, and then we'll use something else to do an inferential test, which really is asking the question, what are the chances that if there is no relationship between your predictor and outcome, what are the chances that you observed one purely by accident? That in fact there's not a real relationship between seatbelts and hospitalizations, but that you saw one accidentally just through random chance. That's what an inferential test is designed to address. I point this out really just to make you a little bit more aware of the complexity that goes into this. I'm not trying to shame anybody for not knowing these things. It's really complicated, and it takes training to understand how to match the phenomena that you're looking at to the statistical test that you would use to calculate and derive statistical evidence for support about a conclusion about the relationship between certain natural phenomena. What we're going to do in this video is focus on the odds ratio, like I already mentioned, and that's because we're working with two nominal pieces of data: a group of vaccinated versus unvaccinated people, and an event, a nominal event, being sick or not, hospitalized or not, dying or not. And that combination puts us in the category where we're using odds ratios and a chi-square test if we want to do the statistical inferential test. So let's walk through an example of odds ratios. And yes, I apologize, we're going to do some math with this. And just to reiterate, again, an odds ratio is really designed to ask the question, how likely is an event to occur in one group versus another? So the example that we're going to walk through, I'm going to leave seatbelts behind for the moment and do something more fun. Let's ask a question like, are people more likely to drink alcohol on a weekend versus a weekday? I would say that the groups in this question are weekend versus weekday, and the event is drinking versus not drinking. And so with this sort of 2x2 combination of things, we can use odds ratios really easily. So we watch 10 people on a weekend, and 9 of them have a pina colada. It's an orange pina colada and blue water. The probability of somebody drinking in this particular sample of 10 people is 90%. Out of the 10 people, 9 of them had a drink. Now I want to differentiate probability versus odds for a moment. The odds of drinking was 9-1. For every one person that didn't drink, that's on the right side of the equation, there were 9 that did, meaning that there was that drinking was 9 times more likely than not drinking. So probability and odds differ a little bit just based on what values go in the denominator, and I'm not going to spend more time on that, but just know that we're working with odds, not probabilities. So this is our weekend group. This is one group. We've got the odds. Now let's look at our weekday people. We only have 8 people in this group, and that's an important thing to recognize. We don't need balanced it would be called like, we don't need balanced membership or balanced cases in either group. We can have more people in one group than another, and that'll be important later on. So that's why I pointed out. So of these 8 people on weekdays, 6 of them did not drink and 2 of them did. So the probability of drinking was only 2 out of 8, or 25%, but the odds was 2 to 6, or 33%. And so drinking was 1/3 as likely as not drinking. That's how we would interpret this particular piece of data. And so now we've got the odds for 2 groups, and we have to take those one step further to get the odds ratio, where we're asking again the question, what's the likelihood of drinking alcohol on a weekend versus a weekday? We're going to take both of those things, and we're going to use this formula. We're going to take the odds of drinking on a weekend and divide it by the odds of drinking on a weekday. Now, this is not complex math. So this is part of why I want to do this video, is even though it may take training to know what statistical information is relevant and how to analyze it, the actual math is not that hard. Anybody with a simple calculator on your phone could run these calculations. So what we're going to do is take that information, the 9-1 from weekends and the 2 to 6 on weekdays, and we'll just divide those together. And what we get is 27.3, which we would interpret as drinking is 27.3 times more likely on weekends than weekdays. So this is hopefully a simple illustrative example of how odds ratios work. And now let's switch gears and actually start to talk about COVID, the reason that we're all here. what I did was went and pulled a bunch of data from the Washington State Department of Health. And so I got this a couple weeks ago and had to compile a few different reports together to create this. But here's the data that we're going to be working with. We've got two groups, unvaccinated and vaccinated people. Now, we do not have equal group sizes in this. In Washington, we're generally a heavily vaccinated state. So we've got 4.2 million people in the vaccinated group and close to 2 million in the unvaccinated group. So they're unbalanced group sizes, and that's okay for this type of analysis. Now what we can do is calculate the odds for all these different cells. And so, we can calculate the odds of testing positive for those in the unvaccinated group between February and July. So sort of a constrained time range. And we can calculate the odds for that, and we can calculate the odds for the same thing happening in the vaccinated group. And I did all that. And what we get is, let me switch this so it works. Here we go. What we get is these odds ratios. And so feel free, pause this, check my math, see if I did it right. Let me know if you get something different than I did. And what we're seeing here is that unvaccinated people were 10.74 times more likely to test positive for COVID than those that were vaccinated. And when we're looking at, what's the rate of hospitalization, we get 48.25 times more likely for somebody that's unvaccinated to be hospitalized compared to somebody that's vaccinated. And you could see that for deaths as well. And so this is what we start to get to when researchers are talking about effectiveness rates or likelihood of being infected or what have you, is they're just doing fairly straightforward math with this type of data. And what we can see is that it's much more likely for unvaccinated people to test positive, which doesn't necessarily mean they were sick. It just is they tested positive, to be hospitalized, meaning they were rather sick, or die, which is not what we want to get to. And so this is why public health officials and politicians and other municipal authorities or leaders are pushing vaccinations, because it's so much less likely for somebody to get sick and die if they're vaccinated compared to somebody that's not vaccinated. Now, as a critical thinker, what we have to do is stop and think more critically about what might we have done wrong. So I showed you the data that seems to, at least at face value, suggest that vaccines are much safer, that vaccines do a good job preventing illness and death from COVID relative to somebody that's unvaccinated. That's like, at face value, that seems to be the conclusion. But what might we be missing? This is really critical for us as thorough thinkers to be aware of what might be going wrong. And so I asked for some input from some people that are against vaccination. Said, okay, what am I missing? Like, if we see this data from hospitals, what else could be going on? Why is this not compelling information for you? And so I have three counter arguments that I want to talk about. The first one is that, regardless of the differential rates between vaccinated and unvaccinated people, just overall, there's not a very high likelihood of somebody getting sick, being hospitalized, or dying. Like for somebody, let's actually go back one slide and look at it. Of the 2 million people that were unvaccinated, only like 9,000 got hospitalized. That's not a very high rate of hospitalization, even if it's way higher than in vaccinated populations. That's just not a lot anyway. And so that's an argument that could be made. I think my response to that would be, sure, there's probably not much individual risk for anyone in particular to be hospitalized or die. But on the whole, still, for a single diagnosis to take up as much hospital space and medical resources as COVID has, it still is a massive public health problem, even if it's not an individual high risk for somebody. And I'm not necessarily talking about people with that are immunocompromised or have other pre-existing conditions. I just mean there's not a high likelihood of getting sick and dying on a case-by-case basis. But across the population, it still is a problem to have that many people getting sick from the same thing. The second argument that I thought was worth noting here is that the PCR testing, which is where they take the stick and they rub it around in your nose and partially in in the back of your brain, it feels like, is overly sensitive. That there's just too many positive tests that are coming out. Not that many people are meaningfully sick. Sure, you might have the virus in your body, but you're not sick with it. So let's stop testing everybody or calling even minuscule amounts of the virus an infection or something. And so that's could be a reasonable claim. I don't really have any data to suggest that this is the case. In fact, I did a video several months ago where I showed that actually PCR testing has the opposite problem. It's way more likely to say that somebody does not have COVID when they actually do, rather than saying that somebody has COVID but doesn't. Is it overly sensitive? I don't know. I'm not a medical researcher. However, if PCR testing is bad, that does not address the differential rates. If PCR testing, let's say that even 50% of the cases of the positive test results aren't meaningful positive test results, that we should just sort of wash away 50% of those, that affects both groups equally. So it's not changing the differential rate between groups, because it applies across all groups simultaneously. So that doesn't actually mitigate the findings that vaccinations prevent illness, hospitalizations, and death. Third one, hospitals are treating and reporting patients for COVID without testing for it or blaming other illnesses on COVID. Again, I haven't looked into this. I don't know what studies have been done to suggest that this is the case. But even if it is true, and this is why I think it's important to bring this up, even if this is true, that should affect both groups equally. So again, it really has no bearing on the question of whether somebody that's vaccinated versus somebody that's not has a different likelihood of getting sick, being hospitalized, and dying. So these are, I thought, the three most compelling counter arguments to it. But I don't think that they have enough merit to overrule the at least face value findings that the vaccinations are in fact effective at preventing COVID. So if we put it all together, here's the big ideas. I think this data suggests that fully vaccinated people are in fact far less likely to be infected, hospitalized, or die of COVID. I just think that's really a plainly obvious finding from the data. The second thing, and this is more of a meta point, but I think is critically important, is that this is difficult stuff. Most of you have probably not encountered odds ratios before or done the calculations for it. And even though we walked through it and it's simple, and I'm sure a lot of you followed along without any problem whatsoever, it's difficult to know that that's the evidence you're looking for in a certain situation. And so I really say that just to bring about humility, that we know we can be tricked by numbers, and it's not a reflection on our intelligence or anything. This is just complex stuff. So stick with it. Keep asking questions. Listen to multiple people, and in particular, find people that are trained as experts in the particular field that you're thinking about, and because they're more likely to have the contextual awareness to know what evidence is good and what evidence is not relevant. Two last quotes that I just think are sort of fun. Mark Twain is mostly credited with saying that there's lies, damn lies, and statistics. That is mostly thrown around, I think, by people that don't know statistics or don't know the worth of it. So I'm a bigger fan of the second one, that statistics don't lie, but liars use statistics. I think a lot of statisticians would agree with that. Now, I am not a statistician, but I think they would agree with this. And even though it's more cynical than I am, I usually don't think people are acting out of malice. I think it's really is a reflection of that second point, that this is difficult, complex stuff. And so rather than saying that liars are using statistics, I think it's really easy for people to be deceived and think that the numbers are telling them something that they don't. So that is it for this video. Thanks for sticking with me. This was a lot longer than I expected, but if you've ever been my student, you're not surprised in the slightest. So thanks for sticking around. I will see you next time. Goodbye.